Welcome you all to this 8th lecture on sequence and series. In this lecture, we shall explore more problems on sequence and series. This is intended to enhance your understanding of concepts that we discussed so far on this topic. Let us quickly recall that AP is a sequence in which difference between any two successive terms remains the same, and this constant is referred to as common difference. An arithmetic progression with first term as A and common difference as D can be represented as A plus D, A plus 2D, so on. In this AP, the nth term is given by the formula A plus n minus 1 into D. We shall denote the nth term by An or sometime by Tn. And sum of first n terms of an AP denoted by Sn has the formula Sn equal to n by 2 into first term plus last term. That is the nth term. Alternatively, Sn, the sum of first n terms, receives the formula Sn equal to n by 2 into 2a plus n minus 1 into d, where as usual a is the first term and d is the common difference of the concerned AP. Here is your next problem, which reads as follows. If S1 is the sum of first n terms of an AP where n is odd and S2 is the sum of terms of this series in odd places, find the ratio S1 by S2. This problem concerns the sum of n terms of an arithmetic progression, as you can see. Without further delay, let us solve this problem. Let A1, A2 and so on be the arithmetic progression. Let us denote its common difference by the symbol D. So, note that the arithmetic progression under consideration has first term A1 and common difference D. Now, let us try to translate the given information using this symbol. What is given to you is the sum of first n terms of this AP. Further, it is given that n is odd. Thus, A1 plus A2 plus etc. plus An is given to be S1. We have a ready-made formula for sum of first n terms of an AP. It is given by n by 2 times 2 into first term plus n minus 1 into common difference, which we denoted by D. Thus, S1 receives this formula. See that S2 is given to be sum of terms of this series occurring in odd places. For clarity, I should say S2 is sum of terms of this series in odd places, that is sum of first terms of this series, first few terms of this series in odd places. Therefore, S2 is A1 plus A3 plus A5 plus etc. plus, since n is given to be odd, the sum under consideration ends up with An. So, S2 is sum of terms occurring in odd places. Let us note that the sequence involved in S2, namely A1, A3, A5 and so on, is again an arithmetic progression. To establish this, note that A3 minus A1 can be written as A3 minus A2 plus A2 minus A1. Using the fact that A1, A2, A3 so on is an AP, A3 minus A2 is the common difference D. Similar is the case with A2 minus A1. Therefore, A3 minus A1 is 2D. Similarly, A5 minus A3 is A5 minus A4 plus A4 minus A3. With a little manipulation similar to what we did above, we get it 2D. Proceeding like this, we can see that the difference between successive terms of the progression A1, A3, A5 and so on remains the same, which is 2D. Hence, A1, A3, A5 so on is an arithmetic progression with first term A1, common difference 2D. Next, the question is, how many terms are there in this arithmetic progression A1, A3, A5 and so on An? It's not hard to see that the number of terms of this summation is n plus 1 by 2. Thus, S2 being sum of n plus 1 by 2 terms of an AP with common difference equal to 2D receives the formula S2 equal to plus n plus 1 by 2 minus 1 times the common difference. N plus 1 by 2 is the number of summands involved in this summation, and 2A1, where A1 is the first term of that AP and 2D is the common difference as we observed. Simplifying this, S2 equal to n plus 1 by 4 2A1 plus n minus 1 times D. Thus, we have the formula for S1 and S2 involved in the question. We can complete the solution by just finding the ratio S1 by S2, namely n by 2 times 2A1 plus n minus 1 times D, which is S1, divided with n plus 1 by 4 times 2A1 plus n minus 1 times D, which on further simplification yields 2n by n plus 1. This is the ratio of sum of first n terms with sum of terms occurring in the odd places. This completes the solution. Similarly, let me remind you that a GP is a sequence where the ratio of two successive terms remains a constant. This constant is referred to as common ratio. A typical GP with first term A and common ratio R can be represented or listed as A, AR, AR square, and so on. Let us recall that nth term of this GP is given by the formula A into R power n minus 1. We shall denote the nth term by An or by Tn. Further, the sum of first n terms of this GP has the formula Sn is equal to A into R power n minus 1 by R minus 1 if R is not equal to 1. If R is equal to 1, the GP reduces to a constant sequence A, and so on. Hence, sum of first n terms will be n times A. Further, let us recall that sum of an infinite GP, namely A plus AR plus AR square plus etc., is a by 1 minus r if mod r is less than 1. If the common ratio has absolute value lying between 0 and 1, then the corresponding geometric series is convergent, that is summable, and its sum receives the formula a by 1 minus r. In the other cases, that is mod r greater than or equal to 1, the series a plus ar square plus etc. is not convergent. We cannot talk about its sum. Having recalled this, let us try to tackle certain problems on sequence and series, more specifically on the concept of AP and GP. Here is your first problem. Pth term of an AP is 1 by q, and qth term of the same AP is 1 by p. Prove that sum of first PQ terms is 1 by 2 times PQ plus 1. It's also given that P is not equal to Q. This is your question. Observe that the problem involves AP. Recall the formulae for nth term of an AP and sum of first n terms of an AP. For the solution, let A be the first term and D be the common difference. Recall that for an AP with first term A and common difference D, nth term is given by the formula A plus n minus 1 into D. Further recall that sum of n terms which we shall denote by Sn is given by the formula n by 2 times 2a plus n minus 1 into D, or n by 2 times first term plus last term in the concerned sum. Having noted this formula, the information given in the question translates to A plus P minus 1 into D, which is the pth term, is equal to 1 by q. Similarly, the qth term, which is given by the formula a plus q minus 1 into d, is given to be 1 by p. Let us designate these two equations as 1 and 2. Recall that for the required sum, what we need is the first term a and the common difference d. Let us try to find this first term and common difference from these two equations. You have two equations and two unknowns, namely a the first term and d the common difference. Let us subtract the second equation from first, which will yield p minus 1 minus q minus 1 times d equal to 1 by q minus 1 by p, which boils down to p minus q times d equal to p minus q by qp. That on simplification yields d equal to 1 by qp, and this gives the common difference for our AP. Using this and one of these two equations, let us isolate the first term. Note that the first equation gives a equal to 1 by q minus p minus 1 into d, that is equal to 1 by q minus p minus 1 times d, which we found out to be 1 by qp. This simplifies to the 1 by q gets nullified, yielding a the first term equal to 1 by pq. Thus, our AP has first term 1 by pq and common difference 1 by pq. Using these two informations, SPQ, the sum of first PQ terms, is given by PQ by 2 into 2 times A, the first term, which is 1 by PQ, plus PQ minus 1 times D, which is again 1 by PQ. This is obtained by plugging n equal to PQ, A equal to 1 by PQ and D equal to 1 by PQ in the formula for sum of first n terms of arithmetic progression. This simplifies to PQ by 2, 2 by PQ, expanding this bracket, it will be 1 minus 1 by PQ, which on further simplification provides PQ by 2 2 by PQ minus 1 by PQ gives 1 by PQ plus 1. Let us simplify further. PQ by 2, this is 1 plus PQ by PQ. Now PQ gets cancelled and 1 by PQ by 2, which establishes the required solution. Let us move further to the next problem. A, B and C are 3 consecutive terms of a GP. Further, a power 1 by x equal to b power 1 by y equal to c power 1 by z prove that x, y, z are in AP. You can observe that the problem concerned consecutive terms of a GP and AP. Here, recall that 3 numbers M, N and P are in GP implies the middle term N equal to root of the product of the other 2 terms. In other words, the middle term is geometric mean of the other 2 terms. Similarly, recall that 3 terms are in AP means the middle term is arithmetic mean of the other 2 terms. Now the solution is immediate. Given a power 1 by x equal to b power 1 by y equal to c power 1 by z, let us assume these equal quantities to be k. Thus, a power 1 by x is k, b power 1 by y is k and c power 1 by z is also k. Taking x the power on both sides, this would imply a equal to k power x. Similarly, one would get b equal to k power y and c equal to k power z. Note that since a, b, c are in GP, the middle term b is equal to the geometric mean of other 2 terms, which same as saying b square is equal to AC. That is, b is k power y square is equal to product of a and c, k power x into k power z. That is, k power 2y equal to k power x plus z. This follows by law of integers. This equality implies 2y equal to x plus z. which reads y equal to x plus z by 2. That is, y is arithmetic mean of x and z. Which is same as saying x, y and z are 3 consecutive terms of an arithmetic progression. This fact we have established in our theory lectures. Let us continue with our next problem. The next problem reads as follows. Let m and n be positive reals. Assume that arithmetic mean of m and n is capital A and geometric mean of m comma n is capital G. Then show that the quadratic whose roots are m and n is x square minus 2ax plus g square equal to 0. As in the previous problem, this concerned with 3 consecutive terms of an arithmetic progression and geometric progression. Let us solve it. 3 numbers a, b, c are in AP if b equal to a plus c by 2 and a plus c by 2 is called arithmetic mean of a and c. Similarly, a, b, c are in GP implies that b square equal to AC, that is b is square root of AC and square root of AC is referred to as geometric mean of A and C. We are given that arithmetic mean of m and n is A, that is m plus n by 2 is A, which gives m plus n is equal to 2A. Similarly, we are given that geometric mean of m and n is G, that is square root of m and n is G, which implies the product mn is equal to G square. Thus, we have m plus n equal to 2A and mn is equal to G square. Let us keep it aside. Now, a quadratic with roots m comma n is given by x minus m into x minus n is equal to 0. Expanding, we get x square minus m plus n times x plus mn is equal to 0, which is a well-known fact. A quadratic with roots m and n are given by x square minus sum of the roots into x plus product of the roots equal to 0. With the given information, we have m plus n is 2a and mn equal to g square. Let us move on. Question reads as follows. If a is arithmetic mean and g is geometric mean, of two positive numbers, then show that numbers are a plus or minus root of a square minus g square. It's very similar to the previous problem, and it concerns arithmetic mean and geometric mean of two positive numbers. Let us recall again that arithmetic mean of two numbers a and b is a plus b by 2, and geometric mean of two numbers a and b is square root of ab. Further, recall that arithmetic mean of two numbers is always greater than or equal to geometric mean, and both coincides if the numbers are equal. Since a, the arithmetic mean, is greater than or equal to g, the geometric mean, root of a square minus g square is a real number. You are talking about square root of a non-negative number. So it makes sense. Let us call the numbers as m and n. Let the numbers be positive numbers, be m and n. Then what is given to us is arithmetic mean of m and n. Thus, m plus n by 2 is given to be capital A, which gives the sum of two unknown numbers which we are seeking for as 2a. Geometric mean of m and n, which is root mn, is given to be g. That gives product of the unknown numbers m and n, which we are searching for, is g square. Thus, the problem reduces to finding two numbers whose sum is 2a and the product is g square, which you might be familiar in quadratic equations. However, let us apply the details. Given m plus n is equal to 2a and mn is equal to g square. With these two, we have to find m and n. Let us recall that m minus n the whole square is m square minus 2mn plus n square, which can be thought of as m plus n the whole square minus 4mn. Thus, given sum and the product of two numbers, we can find the difference of those two numbers. Plugging the value available to us, this is 4a square minus 4g square. So far, our observation is that therefore, m minus n is equal to plus or minus root of 4 times a square minus g square, that is plus or minus 2 root of a square minus g square. This is m minus n. Now we have m plus n and m minus n, from which we can isolate m and n. Let us add these two. To obtain 2m is equal to 2a plus or minus 2 times root of a square minus g square. Isolating m, this gives m is equal to a plus or minus root of a square minus g square. Thus, there are two possible values of m. Taking one particular value of m, namely a plus root of a square minus g square, using one of these equation, we can get n. Secondly, we can take the other possible value of m and find out n, and we will get that the possible values of n are same, a plus or minus root of a square minus g square. Let me leave the details to you. Let us continue. Given f is a function satisfying f of x plus y equal to f of x into f of y for every x, y in n natural numbers. Let f evaluated at 1 is 3. If sum f of x, x is equal to 1 to n, is 120, find value of n. As such, the problem does not seem to be connected with AP, GP, etc. However, note that it involves a summation. Sum x equal to 1 to n f of x equal to 120, which gives in expanded form f of 1 plus f of 2 plus f of 3 plus etc. plus f of n is equal to 120. The question is concerned with a series. Let us proceed to solve it. Note that f is a function satisfying f of x plus y is equal to f of x into f of y for every x and y natural numbers. With this, f at 2 can be calculated as f of 1 plus 1, which coincides with f of 1 into f of 1, that is f of 2 is equal to f of 1 square. Similarly, f of 3 will be f of 2 plus 1. By the property of f given, f of 2 plus 1 is f of 2 into f of 1. F of 2 is calculated to be f of 1 square. So, finally, we get f of 3 is f of 1 cube and so on. Continuing like this, f evaluated at n is f evaluated at 1 taken nth power. This is the observation from the property of f. Now, we are given that summation x is equal to 1 to n f of x equal to 120. This is given. That is f of 1 plus f of 2 plus etc. up to f of n is 120. That is f of 1 plus f of 2 is f of 1 square plus etc. plus f of n is f of 1 power n is 120. The value of f at 1 is given to be 3. Substituting this value, 3 plus 3 square plus etc. up to 3 power n is 120. Thus, collecting all the information given in the question, we end up with this equation: 3 plus 3 square plus etc. plus 3 power n equal to 120. We have to get n out of this equation. Note that the finite sum occurring in the left hand side of this equation is sum of terms of a geometric progression. Do you see that the terms are 3, 3 square, 3 cube and so on? Hence, it is a geometric progression with first term 3 and common ratio 3. The left hand side represents sum of terms of a GP with first term as 3 and common ratio as 3. Let us recall the formula to sum first n terms of a GP. It is Sn is equal to a into r power n minus 1 by r minus 1. This is sum to first n terms of a GP. Using this, we have the left hand side of the equation as 3 into 3 power n minus 1 by 3 minus 1. This is equal to 120. Therefore, 3 into 3 power n minus 1 is equal to 120 into 2, which is 240. So, 3 power n minus 1 is equal to 240 by 3, which is 80. So, 3 power n is equal to 81. Thus, 3 power n is equal to 81, which I can express in terms of power of 3. 81 is 9 into 9, which is 3 multiplied 4 times, and that yields n equal to 4, which solves the question. Let us continue. Find sum of terms of the following sequence. The given sequence is 7, 77, 777, 7777, and so on, up to n terms. One could easily observe that the given sequence, namely 7, 77, 777, and so on, is neither in arithmetic progression nor in geometric progression. So, as such, we cannot use the ready-made formula available for sum of n terms of an AP or GP. However, we shall tackle this problem as follows. Let us denote the sum required to be Sn. Seven plus 77 plus 777 plus etc. up to n terms. Remember, for an infinite sum, we need the notion of convergence, that is whether it is summable or not. In fact, if you consider this sum with infinite terms, then we cannot have a finite value, because the nth term grows arbitrarily as n becomes larger. However, we are not asked to find the sum up to infinity, we have to sum only first n terms. As I pointed out earlier, the difficulty here is that apparently it's neither an arithmetic progression nor a geometric progression whose sum we are familiar with. Let us pull a 7 out so that it will be 7 into 1 plus 11 plus 111 plus etc. When I say etc., here I mean sum up to n terms only. However, the sum inside bracket is not sum of terms of an AP or a GP. So, the issue remains. Let us write it as let us multiply by a 9 and a divide to nullify the effect. Thus, the given sum takes the form 7 by 9 into 9 plus 99 plus etc. The whole point is to introduce an AP or a GP here. With that in mind, let us write 9 as 10 minus 1, 99 as 100 minus 1, and so on. When I say so on, we mean only up to n terms. Now, this is 7 by 9 into 10 plus 100 plus 1000 plus etc. up to n terms, and minus 1 etc. added n times, which amounts to minus n. Now, you can see that a GP has appeared. 10 plus 100 plus 1000 plus etc. corresponds to a geometric progression with the first term as 10 and the common ratio as 10. Therefore, the sum of first n terms of that GP is 7 by 9 into, for that GP is concerned, it is 8 times r power n, r is 10 here, minus 1 by r minus 1, and then the second term minus n. This is the required formula for sum. So, you see, though the given sum neither corresponds to a GP or an AP, it is convertible in some way or the other to a GP, which facilitated us to solve this problem. We shall continue with more problems in the next lecture too. Thank you.